Okay, let us begin chapter 8. And before we begin chapter 8, I will give you a reminder what we did in chapter 3, 4, 7. In 3 and 4, we talked about random variables. In 7, especially, we talked about the unknown population parameter, population mean, and we were trying to estimate it using a point estimate called X bar. And we argued that this X bar is also a random variable from sample to sample. And this random variable either follows an exact normal distribution or an approximate normal distribution, depending upon the parent distribution of X. If X is exactly normal, X bar will be exactly normal. If X is not normal, X bar will tend closer and closer and closer to normal as N gets closer and closer to infinity. This was the result. Now, in chapter 6, you said in descriptive statistics that if population mean is unknown and you want to estimate it, a point estimate of population mean is the sample mean X bar. Now, why we do not stop at the point estimate? Why point estimate is not enough? You read at the screen and you will see it. Yes. Chapter 6, to start the course, we found mean, median, mode, all that. So mean was estimating the population mean. Now, the engineers, they often estimate the unknown parameters like the mean using the sample mean. A single point estimate, such as the sample mean X bar, it does not reveal the reliability of the estimate, how close your estimate is to the actual parameter. You don't know the actual parameter mu. So what is the reliability? What is the precision of your estimate? X bar will not tell you. How precise is your estimate? What are the chances that your estimate will be close to the actual quantity or not? Reporting a point estimate provides no information about the potential error or the precision of the estimate. What could be the potential error in your estimation? How far can you be from the actual quantity mu? Where you don't know what is the actual quantity, but you can estimate that how far you can be from that actual quantity. So we move one step further from point estimate to an interval estimate, or what we call a confidence interval. Here, we will not say that the value of mu is around X bar. We will say it is between this and this. So instead of a single point, we will try to estimate the unknown quantity using an interval. And that interval will be between a lower limit and an upper limit. And you will report the corresponding chances of capturing the unknown parameter as 1 minus alpha. To give you a little more detail about what actually is happening, let me go to this empty slide and let me make a map for you. So suppose you have a random variable X, and here is the population. This population has maybe finite elements or maybe infinite elements. You cannot study the whole population. This population is modeled by a density function or mass function f of x. Depending upon if it is discrete, it's a mass function. If it is continuous, it's a density function. This probability distribution has some unknown parameters. Suppose its mean is there, its variance is there. And suppose you are interested in this mu. Okay. Now, to estimate that mu, which is an unknown quantity from this population, to estimate that mu, what do you do? What do you do? Number one, take a sample. You take a sample. What do you do with this sample? You compute X bar from this sample. And you call this X bar to be a point estimate of this mu. Now here is a real line from minus infinity to plus infinity. And suppose here is x bar. Where is mu on this real line? It can be anywhere. Let's say it is here. We don't know. We don't know. Let's say it is somewhere. How close this x bar will be from mu, we are not giving any idea to the user about that one. What is the precision of your estimate? You are not telling the user what is the precision of your estimate. So only giving a point estimate doesn't tell you the whole story, doesn't tell the user the whole story. Of course, the unknown quantity can be somewhere around this x bar. Yes, we know it will be somewhere around this x bar, maybe on the left side, maybe on the right side, maybe very close, maybe a little far. But whether it is very close, whether it is little far, we are not giving any idea about that one to the user. We are not reporting the precision of our estimate. We are giving the estimate, but how precise is your estimate? You are not giving any idea about that one. Now, to extend this point estimate into an interval estimate, we use the point estimate and we go a little to the right and a little to the left. You add something, you subtract the same thing from the point estimate, and you get what? You get an interval. You have x bar, let's say 10.5. In this 10.5, you will add something, you will go to the right. You will subtract the same thing, you will go to the left. So as a result, you get the two limits. And these two limits, this is called an interval, right? And this thing that you add, it is called margin of error. Margin of error to the right, margin of error to the left. And as a result, x bar plus minus margin of error, it becomes your interval estimate. Interval estimate is nothing but an extension of the point estimate, because you can see in the formula, interval estimate is coming from the point estimate. And maybe at some stage you will get some questions. Point estimate is always in the middle of the interval estimate, because we add something and we subtract the same thing. So point estimate is always right in the middle of the interval estimate, always in the middle of the estimate. So if there is a question where we give you the interval estimate and ask you for the point estimate, how can you find that? Take the middle, the average of two. Take the average of two limits, and the middle of those two limits will be the point estimate. Now, this slide is not covered in your syllabus, but this is for your interest, how we get to the interval estimate of mu. In chapter 7, you said that your x bar minus mu divided by sigma over root of n, it follows what distribution? With what mean? With zero mean and one variance, correct? You said this result is either exactly true or approximately true. This is exactly true if x is normal, and this is approximately true if x is not normal, any other distribution. But this result is true, either exactly or approximately. You call it, let's say, z. Right? Now here is a z distribution to be displayed on the screen. Can you see all of you a z distribution? For this z distribution, I define 2 points, 2 symmetric points, such that the area under the curve between these 2 symmetric points is 1 minus alpha. So the area outside these points is alpha. Half of that alpha is on the left side, half of that alpha is on the right side. Is it visible? The total area under the curve is what? 1. The total area under the curve is 1. I define 2 symmetric points, one of them on the left side, one of them on the right side. Remember the word 2 symmetric points. such that the area inside these 2 points is 1 minus alpha, and the area outside these 2 points is alpha. Now, because these two are symmetric points, so that outside area alpha is equally distributed on the two sides. Half of it goes to the left side and half of it goes to the right side. Now, I'm going to write this whole sentence in an expression. See when I write that. Is this what I said? The probability in a z distribution that z will be between the smaller point, it's just a notation I gave, and the bigger point is 1 minus alpha. Correct? Now, my z is this x bar minus mu divided by sigma over square root of n. So I will plug this z definition inside. I am interested in which unknown parameter? This unknown parameter. So I will manipulate the equation to solve it for mu. I will keep mu in the middle and take everything else to the other sides. To do that, the first thing I will do is I will multiply by sigma over root of n inside the bracket. So I have probability minus z alpha by 2 sigma over root of n x bar minus mu z alpha by 2 sigma over root of n 1 minus alpha. Then I will subtract x bar from all three sides. So I have probability minus x bar minus z alpha by 2 sigma over root of n minus mu minus x bar plus z alpha by 2 sigma over root of n 1 minus alpha. And then I will multiply all the three sides by minus, and the equality will reverse when I multiply by the minus. So this guy will come to the left side. After multiplying by minus, it will be x bar minus z alpha by 2 sigma over root of n mu x bar plus z alpha by 2 sigma over root of n 1 minus alpha. So the probability that your mu will be captured between these two limits is 1 minus alpha, and this is called an interval estimate for mu. The probability that your mu actual unknown quantity will be captured between these two values. Which two values? X bar plus minus a value from the z table multiplied by sigma over square root of n. This is called an interval estimate, and the probability attached to this interval estimate, how much confidence do you have on this estimate, is the probability that your mu will be captured, which is 1 minus alpha. So the confidence level is it's actually 1 minus alpha into 100%. How confident you are about your interval estimate? It should be 1 minus alpha, because that's the probability of capturing your true interval estimate, true unknown parameter. What's in your syllabus is this slide. This formula is given to you in the formula sheet. How it comes, it was derived in the previous slide just for your interest. So a 100 times 1 minus alpha percent confidence interval for mu is given as just an extension of the point estimate. You have the point estimate x bar, you add and subtract something from this point estimate, and you get the interval estimate. And that something that you add and subtract, how does it come? You derived it in the previous slide. This something is called margin of error. Okay, this Z alpha by 2 times sigma over root of n is called the margin of error. Now, in this interval estimate, there are some terminologies that you need to know, because sometimes we give you information in terms of a terminology and you don't know the terminology. For example, measure 1, mutually exclusive. It was a terminology. We gave you in one of the questions that the events are mutually exclusive. We did not directly tell you that the intersection probability is 0. We gave you the information in terms of terminology. So you need to know the terminology. Here in this interval, there are many things that you need to know. Number one, what is 1 minus alpha? 1 minus alpha is the confidence level. So in exam, we might tell you that we want a 95% confidence interval. 95% confidence interval means that 1 minus alpha is 0.95. In exam, we might say we want 99% confidence interval. We might say we want 90% confidence interval, 92% confidence interval, 85% confidence interval. So wherever you see the level of confidence, that's 1 minus alpha. Alpha is called the significance level. So if in exam we tell you that we want a confidence interval where the significance level is 5%, that means we are asking you for a 95% confidence interval, and so on. So either you will be given alpha or you will be given 1 minus alpha in exam. Z alpha by 2 is a value which is taken from the Z table. We call it a critical value. Why? Because it plays a very critical role in determining the length of the estimator, the interval estimate. So this is called a critical value taken from the Z table. How do we take it? I will explain you this computation in one of the examples. And we know is what? It's the sample size. Sigma is the population standard deviation. Currently, I'm assuming it to be known. Although it's a very unrealistic scenario that sigma is known. Sigma is the population standard deviation. Usually it is unknown. But next section will cover the case where this is unknown. But for now, I'm assuming it is known. My interest is in mu, but the second parameter sigma is known. The assumption is that currently it is known. Yes. Last chapter. In this chapter, there are 4 sections. I'm talking about 8.1. Sigma divided by square root of n is called the standard error of x bar. We talked about this one in chapter 7. The distribution of x is called probability distribution, but the distribution of x bar is called sampling distribution, just the difference in terminologies. The standard deviation of x is called standard deviation, but the standard deviation of x bar is called standard error. So this sigma over root of n is called standard error. Remember this terminology. In some questions, we might give you the information using these terminologies. This part that we add and subtract, as I said, this is called what? Margin of error. We denote it by E, margin of error. 2 times this E is what? Go back. This is E. This is also E. 2 times E is what? It's the length of the interval. So maybe we give you the length of the interval rather than E. So remember that the length of the interval, or what we call the width of the interval, is 2 times E. Width of the interval is 2 times E. These are all the terminologies you must know. Must know before going into confidence interval. What is confidence level? 1 minus alpha. What is significance level? Alpha. What is standard error of x bar? Sigma over root of n. What is margin of error? Z alpha by 2 times sigma over root of n. This formula will be given to you in the formula sheet, this one. From this formula, you need to know what is this? Standard error of x bar. What is this? Margin of error. What is 2 times this? Length of or width of the confidence interval. What is alpha? Significance level. What is 1 minus alpha? Confidence level, and so on. Now let's move on to the all-important example. In this example, we are given a scenario that ASTM standard E23 defines whatever. The variable here is the impact energy. this impact energy. And the population mean of this impact energy is unknown. And to estimate that, we have a sample of size 10. 10 values of impact energy. The first thing we need to do is we need the point estimate. And to get the point estimate, we go back to chapter 6, correct? How do we get the point estimate? X bar. To get X bar, we get to chapter 6. And chapter 6 tells us X bar is 64.1 plus 64.7 all the way up to 64.3 divided by 10. And this comes out to be 64.46. To get to the interval estimate, we need point estimate first. So the first thing I did is I found the point estimate. What's the next question? Now read the question very, very, very carefully. What is given in the question? Is it significance level or confidence level? Confidence level. So what's given to you is 1 minus alpha in the question. This implies alpha is what? 0.05. Divide alpha by 2. What is alpha by 2? 0.025. Then to go to the right side of the table, subtract this alpha by 2 from 1. What is 1 minus alpha by 2? You have to repeat these 4 steps to get the critical value. Remember these 4 steps. Get alpha divided by 2. Take 1 minus alpha by 2, which is 0.975. Now go to the Z table. Look for this 0.975 inside the table, and the corresponding value of Z is your critical value. Go to the Z table, look for this 0.975 inside the table, and the corresponding value of Z is called Z alpha by 2. Let's go to the table.
Can we just take a shortcut? Add one, find all over two.
You can do many things.
This just 0.95 plus 1 is 1.95 over 2, 0.97.
Yes. Now, luckily for you, this 0.975 is available exactly. Can you see it? Font size is okay or not? Can you see at the bottom of the screen 0.975 is available exactly? Most of the times this value will not be available exactly. We know it from chapter 4, we know it from chapter 7. That if this value is not available exactly, we will pick what? The closest one. We will pick the closest one. Now the closest one, either we pick the left one or the right one, no problem. Whether you pick the left one or right one, no issue. So against this 0.975, what is the value of Z? 1.96. This is called your critical value. Yes, of course. Of course, they will give you.
Find the number without click F. It's very easy.
I have been studying statistics since 2003. How many years?
Type 1.
22 years. If you ask me to guess the value of Z without Z table, I cannot do it till today.
The measure, we have limited time. Without click F, we take a lot of time to create the measure. So we do.
I don't understand. You don't have control F in exam. You don't have the laptop.
Yeah, that's what I mean. But that's
In lab exam, maybe.
yeah.
But in lab exam, you don't need this table. You have the access to R. R is the table itself. I created these tables and I created these tables in R. So when you have R, you don't need the table.
But I mean, it will take time in the measure. We have.
You talk about major exam. Major exam, we don't give you the access to the laptop.
Yes, that's what I said, because that we take a lot of time because we have paper, we will find a lot of numbers, find things. Take a lot of time.
We're teaching you both ways to do it manually doing table or do it through the laptop in lab exam. You will do that in lab exam on computer tomorrow.
Is just complain. And
Ah.
complain for the major.
Complain after 15 minutes. Okay. Complain after 15 minutes. Now, this is what is given to you in the formula sheet. Now we have all the components of this formula ready to be plugged in. All the components of this formula are ready to be plugged in. Do you have the X bar? Yes. Do you have the critical value? Yes. Do you have the population standard deviation? It should be given in the question. Do you have the sample size? Yes. Everything is ready to be plugged in. So just plug in 64.46 plus minus 1.96. Sigma, I think, was 1. N was square root of 10. N was 10. Square root of 10 is square root of 10. So if I solve these two, one with plus sign, one with minus sign, I get 63.8402 all the way up to 65.0798. This is called a 95% confidence interval for the mean, what was the variable? Impact energy. 95% confidence interval for the mean impact energy. Now we get to the second most important part, how to interpret this confidence interval. How to interpret this confidence interval. Which is question number 3. Interpret this confidence interval that you just computed in part 2. To interpret this confidence interval, remember we will use this statement that we are 95% confident that true mean impact energy is between 63.8402 and 65.0798 J. What is this J? Anyone from joules? Okay. Now, one of the misconceptions is some of you might interpret it as the probability that mu lies between 63.8402 and 65.0798 is 0.95. Can we interpret it like that? The probability that mu will be captured, looking at this expression. Where is the expression here? The probability that mu will be captured between this and this is 1 minus alpha. Can we interpret it like this? This is exactly what I wrote here. The probability that mu will be captured between this and this is 0.95. This interpretation is wrong. Why it is wrong? I will give you the reason. You will probably see one of the multiple choice questions asking you for the interpretation, and this kind of interpretation will be there. I'll give you the reason. This is a classroom. How many students are here? Let's say 35 students. Okay. Out of these 35 students, suppose 10 are from mechanical engineering, 25 from other majors, and I select one student. I select one student. What is the probability that this student will be mechanical engineer? 10 over 35? Not 2 over 3.
2/7.
2/7, yes. 10/35, 2/7. Correct? Correct? I can talk in terms of probability. That the probability that a mechanical engineer will be picked, focus, will be picked is 2/7. Correct? Suppose I picked, and that student is Mustafa, already picked. Can I say that the probability that Mustafa is from mechanical engineering is 2/7? Mustafa is either from mechanical engineering or not from mechanical engineering. I observed it. Now there is no more concept of probability. What is probability? What does probability measure? Uncertainty. Uncertainty is before selecting. After I select, no more uncertainty, no more probability. Now Mustafa is either from mechanical engineering or not from mechanical engineering. No more concept of probability. Gone. Probability is before selecting. Probability is measuring the uncertainty. Before I select, before I observe. Before observing, for any random student, I can say that the probability that the student will be from mechanical engineering is 2/7. Once I select a student, the student is with me. Now the student is either from mechanical engineering or not from mechanical engineering. No more concept of probability. No more uncertainty. Similarly, before observing the value of X bar, before observing the sample, before plugging in the value of X bar here, I can say there is uncertainty. I haven't observed the sample yet. I can talk in terms of probability at this place. Once I observe the sample, plug in the value of X bar. Now this is fixed, this is fixed, this is fixed, everything is fixed. No more concept of probability. Mu is fixed. Whatever it is, we don't know about it, but it is a fixed quantity, correct? Whatever is the population mean, it is a fixed quantity. Once you observe the value of X bar, it is a fixed quantity. Z alpha by 2 is a fixed quantity. Sigma is a fixed quantity. N is a fixed quantity. So after plugging in all the fixed quantities, this lower limit is fixed, mu is fixed, upper limit is fixed. No more concept of probability. What is the output? True or false? Yes. Now about this interval, now either mu is captured in this interval or it is not captured in this interval. No probability. Now we statisticians, we built up another way of saying the same thing, but not in terms of probability, in terms of confidence. We say that we are 95% confident. We don't use the word probability. We say we're 95% confident that mu will be captured between this one. We'll not use the word probability, that the probability that mu is captured between this and this is 0.95. The confidence level is 0.95. So in a sense, what I'm saying is probability this is okay, but this is not okay. After plugging in the values and getting a fixed value, constant value, this is not okay. Before plugging in, this L is actually X bar minus Z alpha by 2 sigma over root of N. This U is X bar plus Z alpha by 2 sigma over root of N. Before plugging in, before observing the sample, before fixing the value of X bar, the only thing which is variable in this expression is X bar. If you pay a little more attention to the confidence interval, in the whole expression, the only variable is X bar. Everything else is fixed. So if you fix X bar also, then everything becomes fixed and there is no more concept of probability. Why? Probability is a measure of uncertainty. If there is no uncertainty, there is no probability. It becomes confidence. Yes. It doesn't become confidence. We use the term confidence. This one. This is correct. We are 95% confident that the true mean impact is between this and this. This is okay. But to use the word probability for this interval is not okay. Again, let us repeat. How to get to the confidence interval? The formula will be given to you. The confidence level will be given to you. One important point. What if we just tell you construct a confidence interval for mu and we do not give you the confidence level? If there is a question where alpha is not given to you, the default value of alpha that you will use is 5%. Remember this one. If alpha is not given to you in question, then the default value of alpha that you will use is 5%. So if we do not give this 95% statement, you will still find 95% confidence interval. So in any question, if alpha is not mentioned, this is true for chapter 8, this is true for chapter 9, this is true for chapter 11, this is true for chapter 12. For the remaining whole course, you will keep playing with this concept of confidence and significance level. So if significance level is not given to you, the default value of alpha that you should use in exam is 5%. Remember. Next question says construct a 99% confidence interval and compare it with the one that you constructed in part 2, which was 95%. So let us first construct 99%. What is 1 minus alpha given to us in this question? Same 4 steps. What is alpha? What is alpha by 2? What is 1 minus alpha by 2? Go to the table, look for 0.995 inside the table, and the corresponding value is your critical value. So let's go to the table and look for 0.995. This one.
We calculate the distance. The first one is 8, and the second one is 6. Shouldn't we take the second one?
Which one?
Uh, no.
Yeah, I'm saying take any one or take the middle of the two. Again?
We have to interpolate now.
No need to interpolate. Either take the closest one or take the middle. No need to do more details. Either take which one is closer. Second one. So just take 2.5, 8 or 9. 8, I think. 2.58. So just take the second one or take the middle, 2.575. No need to go into very much details and interpolate. This is around the middle of these two. So I will take more exact. You can take the second one. You can take even the first one. That is also okay. So take any one. I will take the middle one, which is more exact. So my Z alpha by 2 is 2.75. No, 2.575. 57 and 58. So I'll plug this into the interval. I get a confidence interval. (64.46) plus minus 2.757 times 1 over root of 10. And the interval is 63.6457 up to 65.2743. The question says, is it wider than 95% interval or narrower than 95% interval? Logically speaking, should it be narrower or wider? Wider, why wider, narrower, why narrower?
Because
Logically,
precise. More precise.
it's not precise. You want to be more confident.
Because wider, because as we increase the range, there's more chance.
Yes. Suppose you have not seen the average of first major exam, and I want you to give me an interval estimate of first major exam where you are only 70% confident, not much confident. You will give me an interval, right? 70% confidence interval. Now I want you to give me a 99.9999% confidence interval. I want to be very, very, very confident. If I want to be more confident, then the interval should be wider so that the probability of capturing mu is greater. I want to be more confident. So if the confidence level increases, the width of the interval will automatically increase. So next class, we will try to see the relationship of all of these factors. The relationship of sample size with the width of interval, the relationship of sigma with the width of interval, the relationship of alpha with the width of interval, and the relationship of x bar with the width of interval. We'll try to see the relationship of all of these, how they play a role in widening or narrowing the confidence interval.